More and more, we live in a computer age, a world of vast new technologies. But for all its newness, the basis is an age-old phenomenon, magnetics. From common recording tape to the disks that drive the most powerful computers, all this technology operates on the universal ability of a magnetic bit to align itself in any number of ways with other similar bits. Typically, these bits are composed of one or more metallic elements chosen for their ability to magnetize. Iron and nickel, for example, are excellent magnets. Gold and copper are not. Of course, these bits are infinitely small, as they must be, in order to do their job. So small, in fact, that they're measured in angstroms. A typical bit is 10,000 angstroms, or 1 micron square. That may sound like a lot until you consider that a single angstrom is just 100 millionth of a centimeter, the smallest unit of measurement there is, about equal to the radius of an atom. So these bits are extremely small, but as small as they are, they still take up space. On a typical magnetic disc or tape, they're arranged either as the equivalent of an arrow pointing up, the 0, or an arrow pointing down, the numeral 1. This series of zeros and ones, for example, represent just the letter T. Here's the adjective the, spelled out in this digital fashion, each 0 or 1 representing a single bit. So you see that as small as bits are, they still take up some room, relatively speaking, to accomplish their task. A branch of solid-state physics known as ultra-thin film physics seeks to make these bits even smaller than they already are, so that they may perform their digital tasks in even less space. How much less? Instead of a bit 10,000 angstroms on a side, envision this. A bit just 30 angstroms square, an area that's only 900 square angstroms, over 100,000 times smaller than the area of a current bit, a square micron, or 100 million square angstroms. Think of the possibilities. The same amount of data stored on an infinitesimal smaller space, infinitely smaller in area and in density, capable of revolutionizing an already revolutionary industry. Here's a look into how just such a technology is being created. In a laboratory as relatively small and cramped as the science itself, basic research is pushing back the frontiers of the microscopic world of ultra-thin film physics. Dr. Ivan Schuler is one of its leading pioneers. He and his colleagues have been working in the field for more than a decade.
Our work involves constructing progressively thinner and thinner layers of metallic and semiconducting elements. The objective is to study the limits to which we can pack these thin layers. Since the beginning, the challenge has been twofold. First, to develop the technologies to create such ultra-thin lattices. And second, to understand their properties. What makes them tick? For in the future, we envision practical applications in a number of devices. As we progress, we find that the goals interact. The understanding leads to applications, and applications benefit from the understanding. We are dealing with substances so thin that at their thinnest, they do not behave as we expect. As we progress, we see possibilities.
Just how thin a film is Dr. Schuler talking about? Consider that this is a photograph of the equivalent of a shadow cast by just a single layer of atoms, a lattice in its very earliest stage of construction. To get an idea of how thin that is, consider that a single human hair is hundreds of thousands of atoms thick. Initial success lay in the fact that metallic atoms, like snowflakes, are crystalline in structure, with regular angles. This structural fortuity lets the crystals bond readily to one another in an ordered array called epitaxy. This is a supercomputer animation of just such an ultra-thin layer being created. Individual atoms from two separate metals combining to build a lattice. Note that the atoms are not combining into an alloy. They retain their individual identity as the lattice grows. But at this extreme thinness, their properties are very different. In particular, their electrical conductive properties and their magnetism are not as one might expect. Thus, the lattice has to be built up, layer upon layer of atoms, until you achieve a usable thickness, until you obtain a substance that behaves as needed while still maintaining ultimate thinness. Lattices as thin as 4 atoms thick show unusual characteristics. But for most practical purposes, they must be 15 atoms thick, 30 angstroms, the current minimum thinness for a workable metallic bit on a magnetic disk. Such a lattice could have applications as a magnetic storage disk. In addition, Dr. Schuler's work might have applications in computer hardware as well. As microchips, here again, extreme miniaturization could have far-reaching applications. For as you can build lattices, you can also build super lattices. A typical microchip is composed of metallic elements for their high degree of electrical conductivity. Semiconductors such as silicon and germanium for their unusual electrical properties, and insulators such as any number of oxides for their total resistance to conductivity. Once more, the goal is to make the structure as thin as possible while still maintaining desirable characteristics. Such a superlattice can be likened to a frosted multilayer cake. Ideally, you want to enjoy the taste sensations of both frosting and cake as you eat. But if either is too thin, you'll remove one or the other taste sensation. So your goal is to make the layers as thin as possible in the interests of dietary responsibility, while still maintaining the total taste environment. Whether metallic lattices for magnetic storage disks or superlattices for hardware, all begin the same way, as ultra-thin layers of atoms. The layers are made inside either of 2 unique devices, this sputtering chamber, or this, a molecular beam epitaxy, or MBE chamber. Both achieve the same goal by different means but similar principles: bombardment of a substrate with streams of atoms from the 2 elements that are to form the lattice. The process is similar to that used in ultra-high-speed photography, where the objective is to freeze a rapidly moving object in an instant or less of flight. This is done by exposing the film in the briefest possible instant. The fast-moving bullet is frozen in time, captured in flight, as the metallic atoms are captured upon the substrate, frozen together in a lattice. Here's the process as it occurs in the sputtering chamber. The 2 ion beam guns sputter atoms from their targets onto the substrate, which moves between the 2 beams. The hole in the moving wheel acts as a camera shutter, alternately exposing the substrate to the 2 beams. In the molecular beam epitaxy chamber, the process differs in 2 ways. First, the atoms are produced thermally, epitaxy meaning to bind using heat. Second, the collecting substrate is stationary. A hole in the chopper wheel acts as the shutter. A stationary substrate permits observation of the layering taking place, the purpose for the read gun and screen. Read meaning reflection high energy electron diffraction. Photos of layering in process are taken off a read screen. Different means of layering also produce layers with vastly different characteristics. Superlattices from the MBE chamber, those collected thermally in an ultra-high vacuum, are cleaner, more pure, a vital requirement in the ultra-sanitary semiconductor industry. You can also closely monitor the layering and adjust it as it proceeds using the read screen. Those produced by sputtering, on the other hand, can be built faster in larger quantities and areas. By whichever means, the possibilities are great. A new generation of materials, new magnets, and high-temperature superconductors that would further revolutionize the miniaturization of magnetic disks and systems hardware, all leading to even smaller configurations in future applications in the computer and related industries.